So this is the problem we were working on at the end of class. We were asked to find the area of the shaded region. And I was just going to go over that a little bit again. What we said was, rather than breaking this up into trapezoids and rectangles, we could subtract the area of this triangle from the area of this rectangle, and that would give us the net area. So sometimes you can use subtraction of shapes that are easy to calculate areas to calculate the areas of non-standard shapes. This one's, you could still do it using the area of a trapezoid, but the next problem will be something that it's not quite as simple. So what I did was, I've got a triangle like that, I've got a triangle like that, and I've got a rectangle like that. And so all I had to do was to find the areas of each one of those. And so I'm just going to write down the dimensions of each part. So I have this rectangle, and so I look to see if I've got all the information I need. And I see that the length of this side is 28. So that was 28 centimeters. The length of this side, I look around, oh, there it is, 24 centimeters. So that gives me the area of this whole rectangle. Then I have this larger triangle. So this side, which is the height, is 24 centimeters. And then I need the base of the triangle, which is this part. And that's not given exactly, so I had to do a little subtraction. So what I did was, I knew that this total distance was 28, and therefore this total distance has to be 28. And so if this is 19, this little space has to add up. It has to be 9, so 19 plus 9 is 28. And then once I know this is 9, I can subtract 9 from 39, which gives me 29. So that's 29 centimeters. So there's a saying, things don't add up. That's kind of what relates to these kinds of issues. Besides, in this case, things have to add up to be able to figure out what some of the unknown quantities are. So we have a triangle, a height, and a base, and then we have this little triangle, and we see that they do specify the base, and they also specify the height. So I'm given the height here is 16 centimeters. So all I have to do in this case is just take the area of this. So let's call this 1, this 2, and this is 3. So all I have to do is take area 1 plus area 2 and subtract area 3. And that's what I did. And I did that, well, let's just go ahead and do it. So you get 28 centimeters times 24 centimeters, because the area of a rectangle is just this product of the two sides. I add on this larger triangle, so that's 1/2 the base times the height. So the base is 29, the height is 24, and then I subtract the smaller triangle, which is 1/2 the base, which is 19, times the height, which is 16. And if you plug all those numbers into your calculator, 28 times 24 plus 0.5 times 29 times 24 minus 0.5 times 19 times 16, and I get the same number I got last time, which was 868 centimeters squared. Okay, make sure you get the units right. Is that what I got last time? Yep. So here's another example. What they're looking for is the area in the lower left-hand corner, which is not any of our standard shapes. But if we could use subtraction to find the area of that, then that's going to work out just fine. So what we can see is we have a rectangle or a square. Ooh. We have a square and we have a circle. And so if we take the area of the square and subtract the area of the circle, that will leave these four corners. And because the four corners are symmetric, all these are going to be the same shape and size. They're just rotated 90 degrees relative to each other. Then if I take this total area here, that will give, and divide by 4, that'll give me the area in the little sector, which is, again, not a standard shape that we normally deal with. So let me zoom out a little bit. There's the answer. But how do we get the answer? Well, one thing we have to do is we have to know what the length of the side of the square is. So anybody have any idea what that is in terms of R? So if I, instead of having R here, what if I just had it horizontal? Yeah, so it's 2R, because it goes R that way and it goes another R that way. So that's the dimensions of the square. And because it's a square, well, we know, does it say it's a square? It doesn't say it's a square, but if you have a circle, the only thing that you can draw around it is that. Okay. So what we're going to do is we're going to find the area of the square, and we're going to subtract the area of the circle. Circle. And then we're going to divide by 4, because the area of the square minus the area of the circles are these 4 pieces. Divide by 4 to get one of them. So let's use our formulas that we have. So the area of a square is just the side squared, the length of the side squared. So the length of each side in this square is 2R, and we square that. It's just the width times the height, in this case the same. So that's the area of the, actually that's, yeah, the area of the square. Then we subtract the area of the circle. Well, the area of a circle is pi r squared. Pi r squared. And then we divide the whole thing by 4. And you can see that if I multiply this out, when I square something and the two terms are multiplied by each other, you square this term and you square that term. So I'm going to have 2 squared times r squared minus pi times r squared divided by 4. And then finally, I can factor out r squared. So, and I can square 2, so I'm going to get r squared times 4 minus pi divided by 4, which is the answer that they give up there. So pi, yes.
Right. So where'd you get the 2?
This 2 here?
Yeah.
Because, yeah, because I'm looking for the length of the side of the square. And so if I go from here to one side of the square, that's the radius of the circle. And if I go the opposite way, the same distance, that's the other side. So it's r plus r, which gives me 2r. So anywhere, so I'm taking the radius twice, that gives me the length. And this is also 2r because it's a square. And, you know, pi is 3.1, so that works out good because 4 minus some smaller number, that gives you a positive number. And here's another example. It says if ABCD is a square with each side measuring 36 inches, what is the area of the shaded region? Now, one thing you may look at there and you'd say, well, don't I have to know where this, don't I need to know where this point is here? Because I, you know, depending upon where I define that, I'm going to get, you might think, I'm going to get a different area. But if we look at, if we say this has side length S, and this has side length S, and instead of trying to figure out the area of 3 triangles, what we do is we would find the area of the square and subtract the area of the triangle, and that'll leave the blue stuff. So the area, the shaded area in this case, is equal to the area of the square minus the area of the white triangle. So the area of a square is S, the length of each side squared, just like it was over here. And the area of the white triangle is equal to 1/2 the base, which is, the base is S, and the height is S. And so what we get is S squared minus 1/2 S squared, or just 1/2 S squared. 1 minus 1/2 is 1/2. And in our particular case, S is 36 inches. And you plug those in, and you should get the answer that's shown above, which it will be 0.5 times 36 squared, and you get 648. So it actually doesn't matter where, because you can see what happens even if I have my triangle over here. The base of the triangle is the same, and the height's always the same. So any triangle that you inscribe inside of a square is going to have the same area. In the case of this, if you went diagonally, you'd say, well, the area of the triangle is going to be half the area of the square because it's a diagonal. It's going to cut it in half, which is what we got anyway. But it doesn't matter whether you cut it diagonally or you place it anywhere along there. The area of the triangle, the white triangle, is always going to be half the area of the square, which is kind of a cool math thing. So there's your homework. I think I gave that last time. Yeah, I've already assigned that. It's due next Monday. And the question is, did I push the record button? Yes, I did. Okay, good. If anybody's here today that was not here on Monday, I've got some homework for you. Otherwise, I'll just hand it back to you on the test day on Monday. I don't think there's that many that are here. Okay, I gave that to you already. So we're going to move on to section 5. So just section 5 dealt with two-dimensional objects, dealt with the perimeter and the area. In section 5, we're dealing with three-dimensional objects. So we're talking about volume and the surface, the area of the surface of the three-dimensional object. So it's really just a bunch of formulas. So I'm not going to dwell too much on them. I do have some extra stuff I'm going to talk about, but we'll just go through these things. I'm not asking you to memorize these names. So this is a three-dimensional version of a parallelogram, so that all the sides are parallel to each other. This is a two-dimensional rendering of a three-dimensional object. It's just talking about something like this. This is a rectangular parallelepiped. It's rectangular because if you look at each side head-on, they're rectangles. But it's three-dimensional. We might just call it a box in our normal terminology. And these are called the faces, and these are called the vertices. This is a vertex, the little points on the end, and then you have the edges. So you got a face, vertex, edge. And then you've got these. This is a three-dimensional object made out of triangles. So what we have are, you've got a triangle here. There's one that's laying behind. It's kind of sitting. Sometimes it's hard to visualize what these things are, just because if you're not used to looking at these kinds of drawings, you may not immediately be able to see that. So I'm just going to ask a question. I mean, how many people look at that and think they have a good idea of what it looks like in 3 dimensions? Not so many. Okay. So it's hard sometimes to, unless you have the 3-dimensional objects, to show what those are. It's kind of like a pyramid, except a pyramid has 4 sides. This is a 3-sided pyramid, basically. And it's called a tetrahedron. Have you ever heard of that before? Based on, what's that? Oh, is Dungeons and Dragons? Oh, is it? Okay. You might have, if you ever took chemistry, you know, there are certain molecules that are in the shape of a tetrahedron, like NH3, which is ammonium. Is that right? Ammonium? Anyway, I think that's what it is. The special case of a rectangular parallelepiped where all the sides are the same dimensions is called a hexahedron, which is we call it a cube. Okay. And then you've got these. This is an 8-sided figure, which is made up of 2 pyramids with the bottom stuck together. So that's what this is showing. You can kind of think of this as the bottom of the pyramid, and then you've got the 4 sides of the pyramid, and you just connect them. So all of these different shapes are dependent upon how many sides they have. And you notice here that the octahedron is made up of triangles. So this is one triangle, here's another triangle, there's a triangle there and a triangle there, and you just fit them all together. You fit those 8 sides together to create this 3-dimensional object. This dodecahedron, I think, has, is that 10 sides? 10 or 12, I forget what it is. You can notice that each side is made up of a pentagon. Okay. So anyway, you can look those up if you want to look at, you know, you're not going to memorize that stuff. So what I wanted to do was to talk about how you create these 3-dimensional, what's the word? 3-dimensional shape. I don't want to call them shapes, but you know, 3-dimensional objects, starting off with a flat piece of paper. So if you wanted to create a tetrahedron, you would start off with a piece of paper that's a triangle, it's triangular shaped, and then inside there you go half the way down one side and half the way down the other, and then you draw a line from there to the middle. So you draw lines from the middle of each side, which would create this triangle in the middle. And it would turn out that all these 4 triangles would be the same size. They're just they're oriented slightly differently. And then you would fold the paper along here, and along there, and then you'd fold up the outer pieces, and that would create a tetrahedron. Now, if you want to create a cube, what you do is you make something like this. You draw a square, you stack 4 of those squares next to each other, and then you stack one up and one down. Now you could stack 2 up this way if you wanted to. Yep. We're going to come up and do them. Yeah, we're not going to do that, but hang them from the ceiling. Yeah, it's not high school. So what you would do in this case, again, is you would fold the paper here, you'd fold the paper there, fold it there, put a crease there, fold this up, and then this would be the top of the box. And that's how you create a cube. Now, I'm going to, the reason I'm spending more time, I worked for a paper company at one point in my life, and one thing they make out of paper is boxes. So I looked this up today. Hopefully I can box design for, design for packaging. Pardon me? How to make money out of paper? I can tell you about that. I don't like Yahoo. Let me go to Google. I searched in Google earlier. I don't know. So I found this website, which is pretty interesting. If you want to buy boxes, you can actually make your own box design. And so in this case, you can order a mailer box, you can order a classic carton, or you can order a shipping box. And the way it works is you click on whatever you want to design, like a carton, and so there is your box. Yep. And you can pick your size. So you go up here to pick size, and so I can make my box bigger. And you can see that it's getting bigger, and it changes the dimensions. So apparently it won't do a big box bigger than 4 inches. That's interesting. And then you can put your design on, here you pick the front, put your design, your logo, your drawing, and you can do all the different sides of the box. So you can see what we have here is it's like the three-dimensional rendering of a box. This is the top of the box. This would be the right front. This would be the back. And it flips the box around. And you can get 25 boxes made for $6.57. That's pretty impressive. So I didn't realize they had a thing where you could order your boxes online. Also, let me just show you this. So this is what an actual box would look like that would be printed. So what you do is you take a big sheet of paper, and you would put your design on a printing press. You you take the ink and put it on the printing press, and then it would print on the paper, and you'd get these. Now, you wouldn't just print one of these at a time, because if you put this on a square sheet of paper, you'd have a heck of a lot of waste. You'd have this be wasted. Sheets come in standard sizes. They're rectangles or squares. So if I were to put this on a square, I'd have all this that I'd throw away, and I'd have all this that I'd throw away. The way it works is you would take, let me just show you how this, let me see if I can make this work. Add a page. Okay, thought that would work. Let's try it again. Copy image. Paste image. Okay, let's go to one page. Let's try it again. Copy image. Paste. Okay, so there it is. Then what you would do is you'd create a copy of it, and you would actually, which way? Oh, you'd actually flip this thing around probably, like that. And maybe not. Usually stack these on top of each other. Anyway, I think you'd stick it about right there. Now some of this is you can't see it because it's overlapping, but what you would do, you wouldn't just do one printing. You'd stack multiple of these together so that you try to minimize the amount that you'd have to throw away. So you print more than one box per sheet of paper to maximize the efficiency of the operation. And then what happens is you take, and I got to share this with the group here. It's online. So once you print these designs and stack them correctly on a sheet of paper, you take the sheets of paper, and they have what are called die cutters, and they basically are kind of like knives that would have blades right here, so that it would take this paper and go boom, and it would cut the paper. And so this piece that's not being used would be thrown away, and then you just basically, it's like if you cut it out by hand, but you do that automatically using a machine. Then what you have to do to get these things folded correctly, you need to what's called score the paper. So score the paper, you can almost see it on a book like this, where it's meant to bend. Notice there's how it's indented. Well, you would do that for cardboard. If you take a piece of cardboard, and I didn't bring one with me, what they do is they'll take it, they won't actually cut it, but they'll hit it with a flat piece of metal about that wide. And what it does is it delaminates the paper, which means it doesn't cut through the paper, but it makes the inside of the paper kind of fall apart a little bit. And what that does is it creates a place that you can fold the box without having to damage it. You know, if you try to take a piece of cardboard and you try to just fold it, it goes, you know, it's not very straight at all. So you've got to provide some means of making so it folds along a line, and that's called scoring. So what they would do is they would put score lines here and here and here, so when you wanted to create the box, it would fold easily. And there'd also be a cut right here, because what these things do, right here, 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 that's where you glue things together. Because if you didn't have those flaps, then nothing could be stuck together. So you also have to design in these little flaps. And ultimately what happens is you put glue on this, and you glue this to that, and then it would form a box. And this would probably be glued to, you got to kind of figure out how it all fits together. This would be glued to that, and this would probably be glued to that, and that would be glued to that to create the box. So it's kind of interesting from a, you know, just from a three-dimensional standpoint. How do you create these three-dimensional things from a two-dimensional object? So let's just go back to let's just look at a few more pictures. So here you've got whatever, there's some kind of chicken thing. Again, these are the flaps. These are you have to have, in this case, it's kind of interesting. The bottom is actually where you just interconnect them all. You wouldn't actually, I don't think you glue it. And that was something I saw that was cool too, was, see if I can find it here. No glue. Images. So you can also design boxes where you don't have to use any glue. So instead of gluing it, you take the flaps, and in this case you would take this and fold it over top and put these little tabs into those slots. And the same thing over here. So there's a whole way of designing boxes that don't require any glue. You just need flaps and slots to stick them through. Let's see if there's anything else that looks kind of cool. Oh, I'm going to show you one other thing. So you can also buy chairs that are made out of cardboard. Actually buy these? I guess you could. There are some that are more practical, and then you've got some that are artistic. Pardon me? Can you sit on them? I wouldn't want to sit on that. Yeah. Yeah, some of these I would sit on, some of them I wouldn't sit on. This one, you think that one would break? Let me see if I can find something else here. And So there's this competition every year, apparently, where they design cardboard chairs. Some of them are more artsy, and some of them are more practical. What's that? No comment. Anyway, my daughter, who's the architect, she and her boyfriend, now husband, entered a design into the National Cardboard Chair Competition. I don't think that's the exact one, but it kind of looks like that. They've still got one in their apartment, and they ended up winning the whole thing. They were the 2004 or 5 National Cardboard Chair Competition, and theirs was unique because it was actually more practical than most other ones. Probably so long ago now. It was 2004-ish time. So anyway. Huh? I don't know what the latest 2015, yeah. Yeah, I guess they're still doing it. They got a prize. They got to go to somewhere, I forget where it was. But yeah, still make cardboard chairs. But yeah, you usually get some. Theirs was very practical, even though they were architects. They did. Okay. Anyway. Oh, cancel. So back to this. This is the simplest case here. Well, you can't actually stick it together because it doesn't have any flaps, but it does create a box. And to create an octahedron, which has 8 sides, you take 8 triangles, and you can, again, you would score the thing along these lines, and then you would just fold them together. And then you have a dodecahedron, which actually has 12 sides. Is that 12 or? Yeah, 12 sides. So you were right, it was 12 sides. So I brought in my soccer ball, which is not a dodecahedron, but if you've ever looked at, this is the standard soccer design, you can see it's actually made up of hexagons and pentagons. And I tried to draw one, and I tried to get this was some of the class, I tried to have them fold it and make out a soccer ball, but it's hard to put it together. But, you know, this is kind of a combination of different sizes, different shapes. Pardon me? Can't play catch. Yeah, I'll see if anybody's asleep, and then I'll throw it at them. I think Justin might be out of range there. Either that or I'll hurt myself. Don't want to hit the projector. Yeah, Harley's in the wrong place there. Then you've got this I can't even pronounce it. How many times? 1, 2, 3, 4. 1, 2. So you got 20 sides. They're made of triangles. Okay, so pardon me? Oh, is there really? Okay. Yeah, but with so many sides, it just starts to look like golf ball. Okay, so if we wanted to find the surface area of a rectangular parallelepiped, which is basically a rectangular box, all you have to do is multiply the length times the width times the height. And if it is a cube, which is a force where all the sides are the same, you use the same formula, except that they're all the same. So you just have the volume as s cubed. Instead of length times width times height, it's just s times s times s, which is s cubed. The surface area is the area, as the name implies, that's on the surface. And all you have to do there is find the area of each one of these rectangles and add them up. So we have two that are this shape, we have two that are this shape, and we have two that are this shape. And you just take the dimensions of each rectangle, this length times that length, multiplied by 2 because there's always a front and a back. And that's what the formula says. So 2 times the length times the width plus 2 times the length times the height plus 2 times the height times the width. So those are the 3 ways that you can combine the 3 measurements. The key thing is volume is units cubed because I'm multiplying all 3 together. So if it was inches by inches by inches, I'd have inches cubed. Whereas area, surface area, is just inches squared. It's units squared. Now here's another thing to think about. I can't do it because I have to get some rubber bands, and nobody has. Does anybody have any rubber bands? No rubber bands. Okay. A hair bow. I'm not sure if that. I need a couple of rubber bands. I'll have to do this, demonstrate this next time. But if you take this book and you can try to flip it like this, so I can do that. And if I were to have a rubber band around this thing, it would flip and it would rotate nicely like this. If I took the book like this and I had rubber bands and I rotated it this way, it would rotate nicely, orderly. If you take a book like this, so you have this dimension, and you try to rotate it, you cannot rotate it so it rotates like this. It'll go like start and then it'll go. You can't do it. So I'll demonstrate that next. You can try it at home. So just get a book, put some rubber bands around it, or you could do your phone. So let me show you. I don't want to break my phone, but if I do it this way, nope, I'm not going to do that. How about my calculator? That's not as well. Yeah. So if you rotate it this way, you can rotate it nice and easily. Let me take this off so it doesn't slide up. If you do it this way, you can get it to rotate pretty easily like this. Except I'm not, because it's. Yeah. Well, yeah. But if you take it, so if you rotate it this way, it'll rotate stably. If you rotate it this way, it rotates stably. If you do it this way, you can try as much as you want. It is never going to do it. You can actually prove mathematically that you cannot. You can see how that's nice and stable, and this is nice and stable. But if you try to do it this way, no matter how hard you try. And what the reason is because you can actually, it's an unstable situation. It's kind of like me trying to balance this. If I'm slightly to one side, it's going to fall over. And if it's slightly to the other, it's because the bottom is rounded. It's going, I just cannot. And I might get really close, and it might bounce for just a little bit, but it won't. And the same thing is true in the rotating sense. It may rotate a few times, but when it gets an infinitesimal amount out of alignment, which it will happen, then it starts to go crazy. It won't work. It's an unstable situation. Okay, what did that have to do with anything? Oh, because it was a cube. It was anyway. So those are the equations for the volume and surface area of a box. So you got some problems here. You just plug the numbers into the formulas. So let's just go ahead and do that. So the volume is going to be the width times the length times, what the heck did they use for the height? Yep, I figured that's what it was. width times length times height. You know, which is the width, which is the length? I don't know. There, you know, I guess there's probably some. Let's see, length, width, height. The height's the one that's easy to figure out. I always never can remember which is length and width. You just have to remember to multiply all three sides together, whatever they are. So don't worry about what you call each side. Just know that if you have three different sides, multiply all the three different measurements together. Don't use the same one twice. That's the key thing. So I get 96. And notice I have inches times inches times inches. So you want to make sure that you include the units. Otherwise, it could be 1,000 times bigger. And then the surface area is going to be 2 times 5 inches times 6 inches. So I'm just going up here. I'm going to use these two. Then I'm going to go to the next two. So I'll use 6 inches and 3.2 inches. And then I have to do the last one. Well, I use this one and this one, so I need to do the first and the last. So it's not, I don't have to remember a formula. Just make sure you use all the different combinations. And you plug those in. 2 times 5 times 6 plus 2 times, and you're multiplying by 2 because you have a front and a back, a left and a right, the top and the bottom. But because we're only having inches times inches, the answer is in inches squared. And so I get if I did it correctly, I get 130.4 inches squared. It's worth checking your numbers twice because that's probably the only time you're going to mess up on this is putting the wrong numbers in your calculator and forgetting to write the units down. Okay, the next thing is a right circular cylinder. It's like a can, or like a Pringles can or a soup can. So you've got a round end, and that round end goes all the way to another round end. And the equations are the volume is equal to pi r squared h, and the surface area is 2 pi rh plus 2 pi r squared. So I'm going to ask you guys to think about this. How might they have gotten those equations? So what's pi r squared? Have we seen that before? That's the area of a circle. So here's our circle. And if we take that circle and we just take it and move it a distance h perpendicular to the circle, that's going to create a little cylinder. So you can think of it as kind of like you know, when you're in the snow and you take your arms, and your arms have a certain area to them, and then if you pull them through the snow, you're going to sweep out a distance. And so the volume you create as you sweep your arm is going to be the area of my arm times the distance I move my arm. And so that's all it is. The volume is the area of the area of the circular end times how long the tube is. And that gives you the volume. Now here, the surface area consists of the two circles at the end and the round part of the can. So which one do you think this one is? Is this the well, let's ask you, is this one the ends or the tube part? The ends, right? Because this is the area of the circle. There's the one end. There's the other end. So there are two ends to the can. They're both circular, so that's the surface area. And then the area of the place where the label is on your can, what you have there is it's kind of, in that case, you have the circumference of the ends, and then you pull that circumference a distance, the length of the can. So that's why the second term, 2 pi r, is the circumference of the can, and h is the length of the can. And that's where you get the second one from. So it may look like a complicated expression, but it really isn't. It's just the area of the ends of the tube times 2, because you have 2 ends, and the circumference of the can times the length of the can. So you can plug your, just plug it in the formula. I'm not gonna do it in class. You can do some homework problems. It's just a matter of, in this case, the radius is 5. I can put that in the equation. My height is 7. I can put that in the equation. The volume is going to be units cubed, and the surface area is going to be units squared. So I'm just going to let you do that at home. So there's picture problems where they give you it. There's a word problem. The only trick is they give you the diameter, and the equations involve radius. So make sure you read that. Make sure you've either got diameter or radius and you're using the appropriate one. I make that mistake a lot. I read too quickly. I think it says radius. It really says diameter. Okay, then you've got a sphere, a ball. The volume of a sphere is 4/3 pi times r cubed, which is the radius of the sphere. And the surface area is 4 pi r squared. So a circle was a shape where you had a center. It was in a plane, so it was on a flat surface. And the circle was all the points that were a fixed distance from the center. When you have a sphere, you have the center of the sphere, which is right in the middle of it. And the sphere are the points in 3 dimensions, which are all the same distance from it. We all know what a sphere looks like. It's a ball. So the interesting thing here, we use this in physics a lot. Because if you think of, so here's another physics thing. If you think of light from a light bulb, it starts in this filament in the old days, now just probably some LEDs or whatever, and it's basically this little point. And it radiates that energy out. And it radiates it in 3 dimensions. So all the energy goes out into a big sphere. So if I had a light bulb sitting here, this is a projector bulb, so it's being directed in one direction. But if I just had a light bulb right here, and I wanted to know, how bright is it, or how bright do I sense it a certain distance away? Well, since what you're talking about with a light bulb is energy, and that energy is going out in 3 dimensions. And if I drew a sphere, not a real sphere, but a pseudo-sphere, you think of a light here, and I could think about this sphere like a big balloon that's around it. The energy that's transmitted out it's not being absorbed by anything because it's in air. So the amount of energy that's in this sphere right around the bulb has to be the same as the energy involved in this sphere at this distance, which is the same as the energy in this big sphere that's around it at this distance. And so what you're looking at as far as the energy in that light at different distances depends upon not how much volume, because the light rays are not going through a volume. It's not like it's being absorbed by something. It's transmitting through this big spherical surface area. So it turns out the intensity of light as a function of distance from the source is a function of r squared. If you go twice as far away from something, the amount of energy in the light is 1/4, because it relates to surface area. The same thing applies to sound. If somebody in the middle of the classroom, so I'll get here, so I'm about halfway, so Carly's about halfway between the back. If you looked at the energy in my voice, the sound waves that are traveling, the energy that Harley would hear would be twice as much or 4 times as much as somebody who's in the back row. because the radius, the distance from me to Harley or to the back, she's half the distance. So it's actually inversely proportional to the radius. So you get, and that's of course why you move further back if you don't want to hear something, if you want to protect your hearing. So a lot of things in physics are related to the distance squared, and it has to do with the fact that a lot of things like gravity, sound waves, light waves all become less as a function of 1 over the radius squared, and it's because of this whole idea of surface area. So, you know, to do a problem like this, again, if you're given the dimensions, you just plug it in the formula. So just make sure you can get the right answer when you plug it in the formula. You'll be good. I'll go ahead and work this one. The key thing here is, if you don't think, you'd like, okay, 14.8, I'm going to stick it in there, but that's the diameter, so you're going to have to use the radius. So be careful about that. So the radius is the diameter divided by 2, so the radius is 7.4 centimeters. So the volume is going to be 4/3 times pi times 7.4 centimeters cubed. So we get 4 divided by 3 times pi times 7.4 cubed. And I'll get 1,697 cubic centimeters. Now, you may say, well, I thought you said you should just leave pi. You should just leave pi in there. And the only reason I did that is anytime you have a decimal, you might as well just multiply it out. If you have whole numbers, sometimes it's easier just to leave it as some whole number times pi, but in this case, because the number was a decimal, I decided to just multiply it out anyway. And the surface area would be equal to 4 times pi times 7.4 centimeters squared. 4 times pi times 7.4 squared. And I get 688 centimeters squared. Make sure you use the right units. It's probably the 20th time I've said that, so make sure you use the right units. Okay. A right circular cone. So that's like one of those paper drinking cups that's in a conical shape. So you have something that's circular, but it goes to a point. There are things in life that are actually cones, besides ice cream cones, or well, see, that's a little bit different. I mean, with a flashlight, what you have is, if you've ever taken a flashlight apart, is you have the light, which without the reflection, without the reflector in there, it's going to create a, it would just go out in all directions. So here's another little physics thing for you. So if you have, so let me explain how a flashlight works, because it definitely is not a cone necessarily. It might be like, sort of like a cone. I'll explain why it's not a cone. So here's my flashlight. You have a light bulb like that, and then you have this reflecting surface behind it like that. And so these light rays are just going to go straight out from the light bulb. And if I didn't have the reflector, they would just go in the other direction. What happens is the light comes here, and then it bounces off the reflector, and it goes like that. And then this one bounces off the reflector and goes like that. So depending upon how long this cone is, you know, where the light is contained in the flashlight. And this is a two-dimensional picture, but a flashlight is actually three-dimensional. And it's probably not a, and so is the question is it a cone shape? It's probably sort of like a cone shape, but it's not exactly cone shaped. But what this does is it just makes it so that all the light energy gets bounced out to the direction that you're interested in. So that's how a flashlight works with the reflections. These just go straight out and these bounces off. And there's probably some, optimum location from the, some place where the light is the brightest, but it's probably not going to go out straight. It probably is some kind of an angle to the whole thing. Anyway, back to a cone.
So we're just talking about solar plants. This is an example of a solar plant. They're not using parabolic reflectors, they're just using plain reflectors, and they reflect the light to a central tower, and all that energy is concentrated on a spot, which is where the energy is used, basically changing water into steam. So this is in the Mojave Desert in California. And if we click on this figure here, you can see a picture of it. So these are all the all the mirrors, and then this is the central tower where all the energy is concentrated. And the amount of energy is such that it heats up high enough to boil water. So the question is, how many reflectors are in this collection of reflective mirrors? It was in the, so you can just back up a little bit and read that. Well, I will just back up for you. So you're going to tell me that there are 173,500 heliostats, each with 2 mirrors. That's interesting. So it must have some way of focusing it. That must be why there's 2 mirrors.
So the equation for the volume, it's 1/3 pi r squared h, where r is the distance from the center of the cone, which is the the circular part of the cone, to the edge of the cone at that point, and the height of the cone is from that point to the point. So what you have, pi r squared is the area of this circle. If I took pi r squared h, that would give me the volume of a can, but it's not a volume of a can because it's a can that starts like this and then comes down like that. It's almost like the circle, the cross section of the end. If I took this and I cut it into little pieces, as it goes down, the outside of the cone would go like that, and then it would come into a point like that. So it'd be like that. It's like an three-dimensional MRI of the cone, like that. So it's got to be less than a can because I'm reducing the area. You might think it's a half, but because it's closing down in 2 dimensions instead of in 3, it's closing down in 2 dimensions, but not in 1 dimension. It's not a half, so and then the surface area is just pi times r, the square root of r squared plus h squared, plus this pi r squared. That part is the end of this is the surface area of the circle at the end, and this part is the surface area of the part that goes around like that. So this is the end of the cone, and this is the surface of the cone. This is the length of the hypotenuse. The square root of r squared plus h squared is going to be that distance. So it makes sense that that should be included in there. Anyway, those are the formulas. If you need them, you can look them up. Make sure these are cubed units. Those are squared units. And the final shape is a pyramid. And don't think you're leaving yet. So I keep hearing zippers going here. But so the volume of a pyramid is 1/3 the area of the base. So it's this area. So if it's square, then you'd multiply the two side lengths together. And that would give you the area of the base. If it's a rectangular pyramid where this side is different than this side length, then it's still the area of the base times the height times 1/3. So it's very similar to it's basically the same, I think. Let's go back and look at it. If we look at this versus the cone, this is 1/3 pi r squared h. Pi r squared is the area of this thing. So we've got 1/3 the area of the base times h. So in some ways it's almost exactly the same as the right circular cone. So the volume is 1/3 the area of the base times the height of the pyramid. Again, you can plug numbers in as well as I can. I'm not going to. So for the simple calculations, just do the homework problems. We're going to look at a few word problems just to do a little harder thinking as far as using some of these formulas. Yes? Yeah, there is no, they don't give us the surface area for a pyramid. You could figure it out, but I think it's kind of, you'd have to know the dimensions of each side, whereas for the volume of a pyramid, we just need to know the area of the base, which means it could be any combinations of lengths just so the product equals B. But the surface area would depend upon the length of this side and the length of that side, and I think it gets too complicated, so they decide not to cover it. So for the test, when you look at the review, what I'll say is write down the formulas and be able to plug them into the equations. Okay, it's kind of trivial, but that's what's in the book. So I'm not going to ask you to memorize them. Just write the formulas and know what each term means and be able to use it. Okay. So I'm skipping that too. So this is problem 51. It says a plane intersects a sphere to form a circle, as shown in the figure. If the area of the circle formed by the intersection is 576 pi inches squared, what is the volume of the sphere? So we're basically taking a round ball and we're going to cut it at some distance. In this case it says 7 inches. Okay, so they give you the distance. It's saying it's 7 inches from the center of the sphere, which I can't show you because it's inside, to that point where you create the circle. So the sphere has to be more than 7 inches or it wouldn't be inside. So to be able to calculate the volume of a sphere, we need to know what the radius of the sphere is. The volume of a sphere is 4/3 pi r cubed. You can look up the formula. So what we need to do is figure out what r is based upon the information given. And it says the area of the circle formed by the intersection. So what that means is if I chop this off, you would have, the top would look like a circle. Where I've chopped it off, you think it's somebody's, like you see those things, Monty Python, where they chop off the brain, where they chop it off, and then you'd have the part that's the circular part would have an area. The actual circle that I create, that has an area. So basically what you have to do in this is you take the area that's given, and the radius of this circle here is going to be able to, you can use that to calculate the radius of the circle, which goes from here, not from the center of the sphere, but from the center of this circle to the edge of the sphere. So we can calculate this distance first, then we can use the Pythagorean theorem, because if this will be one side of a right triangle, this will be the other side of the right triangle, the hypotenuse will be the radius of the sphere, And once we have the radius of the sphere, we can just plug it into the formula for the sphere and get the answer. So here's how it goes. So again, what we're doing is you've got this circle right here, and we know the area of that circle is given to be 576 pi inches squared. And I'm going to use some, and let's write this. And we have this triangle that I've created. This is the radius of the sphere. This is 7 inches. This is, we'll call this capital R. That's the radius of the circle that we have here. So that's the radius of the circle. This is the radius of the sphere. So the area of the circle, we used stuff from the previous section, is equal to pi times the radius of the circle squared. So it's this radius that I'm using. So what I can do is I can solve for R. The area of the circle is 576 pi inches squared, and that's equal to pi times R squared. So I divide both sides by pi, and so the pi's cancel out here, pi's cancel out there. I get that R squared is equal to 576 inches squared. And then you can take the square root of both sides. And the square root of a product is the product of the square roots. So I would take 576, take the square root of that, and I would get 24. So I get 24, and the square root of inches squared is inches. So that's my radius of my circle, 24 inches. Then what I can do, I don't know what I did there, undo. Okay, add page, there we go. So now I have the Pythagorean theorem. I can solve for R. So I know that R squared is equal to 7 inches squared plus now 24 inches squared, which I've quantity squared. So I'll take 7 squared is 49, so you get 49 inches squared plus 24 squared, which is 576 inches squared. You add those two together, 576 plus 24, 49. And I get that R squared, which is the radius of the sphere, is 600, so it's 625 inches squared. Take the square root of both sides, and the square root of 625 is 25, and the square root of inches squared is inches. So that's the radius of the sphere. That's the distance from the center of the sphere to the edge, to the surface of the sphere. R is the distance from the center of this circle that I create. And therefore, what they asked for, what was the volume of the sphere? Well, the volume of a sphere is equal to 4/3 pi r cubed, which is the radius of the sphere, and they have it in terms of pi, so I'm going to leave the pi in there. So now all we have to do is just plug in the known value of r. So we have 25 cubed, and so if you take 25 cubed times 4 divided by 3, you get 20,833 pi inches cubed, which, let's see if that's the right answer or not. Well, they said 62,500 divided by 3, which is 20,000 times 3. 62.5, yeah, so that's right. So that's how that problem works. You had to use the known area of the circle to get the radius of the circle, and then you could use the radius of the circle with the height above the center to create a right triangle, and then you could use the Pythagorean theorem to find the find the radius of the sphere, and then you could use the equation for the sphere to find the volume of the sphere. I'm not going to put something that hard in the test, so don't worry. It's just for you to think about how you might not know how to do these problems, and hopefully me explaining will say, oh yeah, okay, I kind of get that. I would have never got it otherwise, but hopefully you kind of follow me along there. And I'm going to go ahead and give you the homework assignment for this section. And what we'll do is after the test, we will just go through a few more examples that are more challenging and just to stretch your brain a little bit. So these actually, you're responsible in section 5 to know what the formulas are, but you can write those down in your equation sheet. And if I asked you to do a calculation where I give you the numbers, you just stick them in, you make sure you do your calculations right, and you put the units on the answer. Put the units on the answer. No excuse for not doing that. So we're done now. You may now. And I guess we got 4 weeks left now. What's that? Where's time go? Okay, for you guys online, you may now say goodbye. And